And as part of the QDC course, we teach a number of different languages. So there's KDB as well for high frequency trading and market data. There's also C++ as well. But one of the other courses within the QDC, which I teach, is on Python. So I'm going to talk to you basically about why Python is good for finance. And I'm going to give you a few coding examples as well. So I'm going to use this Jupyter notebook essentially to present. Okay. I'd make this full screen as well. All right, so Python for finance. Just take a sip of tea just before I start. So I always end up speaking for a long time and then not actually drinking anything. So I'll periodically stop just for a short pit stop throughout the course. So just a bit about me. So I've spent 15 years in FX. I started at Lehman Brothers, which is alas no more. And later I was at Nomura as an executive director. And I've been developing systematic trading strategies basically my whole career, mostly in FX. I've got a number of different open source libraries, which are pretty popular on GitHub for finance. So FinMarketPy for backtesting trading strategies. And in the course, we actually use this quite extensively. FinDataPy for downloading data, and also ChartPy for doing visualizations. I've also done quite a bit of work around transaction cost analysis as well. And I'm also one of the co-founders of Talesians, one of the co-sponsors of the course. And at the moment, I do a lot of my consulting work through QMacro. And there's a few of the books that I've contributed to as well below. So what's the outline of today's session? I guess the key crux is why do we want to use Python to analyze markets? That's the key point. We'll also discuss some of the useful Python libraries for financial analysis. And if we get a bit of time towards the end, we might be able to do a few demos as well in Python at the same time. So why do we want to use Python to analyze markets? Essentially, you have conflicting objectives because we want to compute stuff very quickly. We want to execute quickly on our CPU, but at the same time, we want there to be a fast development time as well when we write code. So fast shouldn't just refer to how fast we execute. It also refers to how quickly we can write the code as well. So compared with Python, something like C++ is obviously going to be very fast. There's no doubt about that essentially C++ is a lot faster than Python typically. But it might take you a bit more time to write a large system in C++ by comparison. There's other languages as well, like R, and it has a lot of statistics libraries. But I would argue it also suffers from a speed issue to some extent, and it's also not really suited for large systems. Julia, which is a newer language, is supposed to be faster, although there's still a bit of debate about that, but it still doesn't have quite as many supporting libraries as Python. And a lot of times, if you use Julia, you're probably going to end up relying on Python libraries underneath anyway. There is also KDB that can be used to backtest trading strategies, but it can be tricky to use for some other tasks as well. So it's highly specialized, essentially. So definitely a good thing to learn, but it's focused towards high frequency tick data and analysis of that. There is also a way of using Q with Python as well. So that's like a nice combination, actually, particularly when it comes to visualizations. So essentially, you can think of Python as a bit of a compromise. It's a general purpose language, unlike R. It's also quicker than R, but at the same time, admittedly, it's not as fast as something like Java or C++. And you can use it to engineer large systems as well. It supports object-oriented coding. There's lots of libraries available to play with data with Python. We'll talk about some of them later on. And it can also help us bind and glue together code written in different languages. So we can call code written in C++. We can also work with Q as well with Python. So it's quite a nice bridge, essentially, between other languages. And I'd argue that computation is getting cheaper all the time, especially with the cloud. And there's all sorts of tips and tricks as well that you can use with Python to speed it up as well, which is relevant, I think, if you want to make it quicker. So the next step is to talk about some of the useful libraries that we have for data science in Python. So obviously, you have the main Python language and you have the standard Python libraries, which come with every variant of Python. But then there's a plethora of so many third-party libraries that people have written. So Obviously some of mine, but some of the most popular things like pandas, NumPy, and so on. And we'll talk a bit more about them shortly. So what are the core libraries for data science? Essentially, the core libraries consist of the SciPy stack. First of all, you have the IPython environment, the interactive console for Python, essentially now part of Jupyter. So this is actually a Jupyter notebook, which I'm using at the moment, albeit in kind of like a slide format. Then we have probably the key library, I would say, for data science, which is NumPy. So this adds support for doing operations on things like vectors and matrices and basically n-dimensional arrays. And this is a lot quicker than using for loops to do your arithmetic operations in Python. Pandas, which is probably the library I end up using the most. So this is a library for time series analysis. And this actually grew out of the work at AQR, which was done by Wes McKinney, who's pretty well known in the Python community. It provides a lot of common operations, things like doing aligning of time series, joining, and general sorts of calculations. So I remember when I was at Lehman, so this was about 2006, 2007, I remember I spent ages writing my own time series library in Java, and it took ages. But now I'd never dream of basically writing my own time series library because you already have Pandas, which is really comprehensive and does pretty much everything that you want. There's also confusingly SciPy, which is the same name as the stack, and this has operations for numerical analysis and optimization. And I've used it, for example, for fitting like PDFs and things like that as well. SymPy, which is the only one here that I haven't used, is for doing symbolic mathematical operations. So if you want to do like symbolic integration and stuff like that. But all these libraries are basically the backbone, I'd say, of data science in Python. So if you do data science in Python, you'll definitely have used one of these libraries throughout your career. So one of the key things I always say with data science is not just about the analysis and getting the results, it's also presenting the results as well. So part of the issue is if you go into a client meeting or go to your boss, they probably don't want to see hundreds of pages of tables, basically. I don't like seeing that either. What we all like to see is nice visualizations, essentially, to try and show and present what we've done in a kind of a cohesive and easy to understand manner. So visualization is something that you can do very effectively with Python. And there's lots of choices as well in terms of visualization libraries. And this actually is only a small list. I think there's probably a lot more actually out there than what I've listed. So one which is quite popular, or used to be, I think, probably more popular, is Bokeh. And this is a JavaScript-based library. So basically you can create interactive plots which are stored in HTML files. Probably the most well-known, I would say, of all the visualization libraries is Matplotlib. It can be, I'd say some of the syntax can end up being quite complicated if you want to do something quite specialized, but it's actually quite a flexible library. And I'd say most people end up using that. My visualization library of choice probably at the moment is Plotly. It allows the sharing of charts as well to the web or in a private environment. But the key thing is these days, over the past few years, they've transitioned so you can also use it offline without having to share your charts. It's also accessible for many languages, things like R and MATLAB. I think they also have a Java wrapper as well. So it's really like a nice cross-platform library. VisPy, which is a very specialized library, and it's not really quite as mature as a lot of the others I've talked about. So this has GPU accelerated plotting. Plotly also has some GPU accelerated plotting in it as well, but VisPy is specifically designed for that. So if you want to plot like that, millions and millions of points, Matplotlib will probably crash on you. But then VisPy is something that you can use, but I found it a lot more difficult to use in practice. And if you can't really decide which library to use, there's ChartPy, which I've written. And this ends up being a wrapper on top of Bokeh, and in particular, a wrapper on top of Matplotlib and Plotly. So it allows you to quickly change between Plotly and Matplotlib by just changing a keyword. So, and I've tried to make the API a bit easier to understand as well. So I typically just end up using ChartPy these days on top of Plotly or sometimes Matplotlib. Sometimes I'm in a Plotly mood. Other times I'm more in a Matplotlib mood. It just depends upon what analysis that I'm doing in practice. Machine learning, so that's the buzzword at the moment, right? And you have many different libraries for machine learning and statistics. So There's Talesian's TSA, which has been written by Paul Billicon. So he's one of the other lecturers on the QDC. There's also Quanticon, which is basically an econometric library. And then you have quite a few specific machine learning libraries as well. So things like TensorFlow, which has been created by Google, PyTorch as well. Probably the machine learning library that I end up using most is probably the simplest, is scikit-learn. And it has all sorts of regressions and classification techniques. So some of them are obviously fairly standard, things like logistic regression for classification and linear regression as well. And you can do things like OLS and ridge regression, and also has a lot of nonlinear models as well. And I'd say it's fairly good place to start if you want to do some machine learning, essentially. And TensorFlow, they keep on making it easier to use, adding new interfaces and stuff. So that's an interesting thing to look at. But I would say probably as a first choice, maybe scikit-learn if you're doing machine learning. At least I've found it relatively straightforward to use. So one of the aspects of Python, which I mentioned, and everyone will probably say it if you say that you're learning Python, is that Python is actually quite slow in practice. I think there should be a recording of the webinar just in answer to the question. So this is being recorded. So and I think WBS will share this later on. So basically, Python is not that quick. So what can we do to make it quicker? So Python historically has been the way to go. So it basically has a subset of Python code which can be compiled down into machine code essentially. So this code will get converted into, will end up getting compiled and then dumped into machine code. So this is going to be very fast. And some of the code in, say, Pandas is actually written in Python underneath. A newer technique, though, for kind of speeding up Python code is the use of Number, which has a low-level virtual machine. In this instance, you don't actually need to run it through a compiler beforehand, essentially. But you do need to write your code in a specific way so that's supported by Number. So Number understands, for example, calculations on NumPy arrays. It doesn't understand calculations on Pandas. But the key point with Number is you can end up doing for loops, just like with Python, but it's a lot quicker than Python. So sometimes you just find it very difficult to write code without for loops. Number is actually the solution for that. And I've managed to get really massive speed ups by using Number. It does take longer to write code, which is compatible with Number in Python. But if you have a specific bottleneck in your code, I'd strongly recommend looking at Number. And it's I've got good feedback from a lot of people who have also used Number as well at the same time. You can try to use some of the parallelization features in Python. So one of the modules which is included is threading, and there's also multiprocessing as well. The point with threading is that typically it's used for speeding up IO-intensive operations. So by IO-intensive operations, I mean things like reading from disk, downloading web pages, etc. And you can make parallel requests using threading. But underneath, it doesn't actually do computations at the same time. If you want to do computations at the same time, which rely upon a lot of CPU power, potentially like doing Monte Carlo simulations or something like that, another solution is to use processors. And with processors, literally what it does, it creates another Python instance on your machine. There is some overhead in terms of creating processes, but in many cases, it will be worth it if you have a computationally intensive operation which you want to be parallelized. There's other ways of distributing tasks as well, things like Celery, which allow you to kind of distribute tasks not only on your own machine, but potentially across the whole cluster. There's also async IO as well for doing asynchronous IO operations. It's kind of like a wrapper on top of threading. And another nice library, if you're dealing with very large data sets, is Dask. And it's got some features for doing task scheduling, but it also has a pandas-like interface for using working with data frames. So the problem with pandas is, let's say we have a data set which is huge, I don't know, 100 gigabytes or something. That's not going to fit in your memory to do computation in pandas, right? So the only way to use pandas is potentially to batch those computations. But that means you have to rewrite your code and it will end up getting a bit messy. Alternatively, you can use Dask, and Dask will do all of that batching for you. instead of pandas. So it will just do it in the background, create a computation graph essentially for execution, and you don't need to think about that. So you can basically treat a massive file and just load it up into Dask and do time series operations on it, and just use it as though it's in memory. But underneath, Dask will end up doing operations basically to do the calculations in the background. Another good use of Python is for doing processing with text and natural language processing essentially. And there's lots of choices here that you can use. So NLTK is probably the oldest of and most well-known of the natural language processing libraries in Python. There's also Spacey as well, which replicates a lot of the operations of NLTK, but it's built on top of Cython in many instances, so it can be a lot quicker. There's TextBlob, which is a wrapper on top of NLTK, which makes it a bit easier to use. Another library from Stanford for NLP is OpenNLP. And there's a newer library called Transformers, which has a lot of the state-of-the-art models that we have in natural language processing, things like BERT, GPT-2. I don't think it has GPT-3 because that's closed source. But if you go to the website for Transformers, I'll have hundreds and hundreds of different pre-trained NLP models that you can play with. And a lot of them will be for specific applications like product reviews or potentially looking at financial text and so on. And I would say Transformers is pretty cool as a library to use. Another key point is if you need to get text, typically involves web scraping, and Beautiful Soup basically helps you to clean up web scrape text. And if you don't want something open source to use, you have things like Google Cloud, AWS, IBM, Watson, etc. And they offer NLP services on the cloud as well, if you want to at the same time. So one of the aspects of doing stuff in Python is you want other people to use it, right? That's no one else uses your code, and you probably get a bit of a dead end. So you can basically expose your Python code to a web page, and there's many different ways of doing that. So one of the ways that I've used is Flask. So it's like a mini web server essentially. And on top of that, there's Dash, which is a library that's been developed by Plotly, and it makes it pretty straightforward and easy to use to create web dashboards. And that's one of the things we cover on QDC actually, creating web dashboards with Dash. If you work in a bank or any sort of financial institution, there's no getting away from Excel. Everyone still loves Excel. Even me, been coding for many years, I still use Excel quite a bit because it's all visual, and I'm kind of find it easier to use essentially. So the question here is: C++ the only alternative for speed over Python, or does Python have a Python C++ hybrid package? Well, I guess there's many ways to speed up Python. So some of the ways I mentioned are things like Cython, which basically convert a subset of a superset of Python code into C, which can get compiled to machine code. There's Number as well. Something that I haven't mentioned is there's a different Python executable called PyPy. Let me put it on the chat actually. And this is actually a lot quicker if you run your code through this. The only issue is it's not going to be compatible with all the Python packages that you want. So I typically just end up using CPython because of that. It just ends up being easier to use from that aspect. We also have Selenium in terms of web scraping. We have things like Selenium, Scrapey as well, and Twython. So Twython makes it easy to basically access the basically Twitter's API. But one thing you do need to know when you're accessing Twitter's API is that you're limited to the number of tweets you can download. So if you want to have full access, you have to actually pay a subscription fee for that. There we go. So a big part of financial markets is actually storing market data. If we don't store market data and other sorts of data, we're kind of a bit stuck. We can't do anything. So these are some of the ways that you can get access to data. So there's Arctic, which is basically a nice wrapper on top of MongoDB, which makes it easy to store time series in MongoDB like pandas data frames. If you want to access data from an external source like Bloomberg, Bloomberg have got an API for Python called BLP API. There's all sorts of libraries as well for accessing databases like PyMongo. There's also SQL Alchemy, which I've not written here, which makes it easy to access SQL databases through Python as well. In terms of other market data providers, obviously Bloomberg is one. You also have Refinitiv, which have a nice API as well. Quandl, which is now, I think, part of NASDAQ, also have a nice API as well. So some of the data from Quandl is free, but quite a lot of it is also paid. If you want to mix and match between Q and Python, QPython is a nice library to have a look at. And if you want to cache data, I would recommend using Redis. So Redis is an in-memory database, essentially. So I use Redis quite extensively for caching data. So I don't keep on hammering my database. I'll just push it to Redis temporarily so that I can keep it in memory, essentially. So I'm going to talk a bit about the process where I've developed libraries for financial markets. So essentially, when developing these libraries for financial markets, things like FinMarketPy, FinDataPy, etc., I was trying to think about what are the parallels between data science problems and developing trading strategies. Oh, so somebody put on chat, I can use Impala as well for in-memory. I think so, but I've not used Impala for doing in-memory caching. Yeah, by all means, Redis is not the only in-memory cache. There's lots of others. There's also I've also used Memcache as well. So there's a multitude of different in-memory key value stores, essentially. So I'm just going to outline a few of the generic steps we might undertake when trying to solve a data science problem, or indeed developing a trading strategy. So the first step is that we want to form some sort of hypothesis, whether it's a data science problem or it's a trading strategy. The second step is that we need to find data. And typically we'll get this from the market, although increasingly we might try and look at alternative data sets, which are sourced from outside the market as well. And then the third step is that with our hypothesis and our data, we want to use statistics to check our hypothesis. So this basically involves backtesting a trading strategy. And just in answer to the question on the chat, this session will be shared for everyone that's signed up in terms of the recording. And then the final step 4, will be that we'll want to present our findings. And usually this involves some element of visualization. So I started creating a Python library, PyThesis, over it's more than 2 years now. It's actually quite a few years now. And I ended up rewriting it and basically splitting it into a number of different libraries. The main reason is generally when you write an open source library, you want it to be relatively focused, particularly the most popular ones. You don't want a library which does absolutely everything because people find it confusing in terms of what it does. So you want to do one thing particularly well, I guess, with a library. So I've built several of these libraries. The first one is ChartPy, which is for visualization, allowing you to basically do charts with multiple backends like Plotly and Matplotlib, which you talked about. We also have FinDataPy, which allows us to access market data from many different sources as well. And then FinMarketPy, which is for backtesting trading strategies, essentially. I guess I should have chosen a bit more, kind of made the logo slightly different, but maybe that's for another day, I suppose. So. And I guess the key point when you're developing a library is that you want to have some element of abstraction. So there's a lot of choices of the underlying libraries that we want to use. If I'm downloading market data, do I want to use BLP API, Quandl, or the Icon library for Refinitiv, etc.? When it comes to visualization libraries, which ones do I want to use? Do I want to use Bokeh? Do I want to use Plotly, Matplotlib, etc.? Essentially, what I want to do is I want to abstract away the general plumbing for accessing market data. Otherwise, our code will end up extremely messy. Every time I want to switch between market data providers, I'd have to rewrite all my code. So what I want to do is I want to separate out the plumbing, i.e. the various vendor-specific APIs, from the underlying data science problem. Then, as a researcher or a trader, I can concentrate on developing the trading strategy rather than learning a different API of a different vendor every day, basically. And it makes the code easier to maintain and update because we can just add new underlying libraries and data sources when they become available and slip them into our code base. So when we're doing back testing, we need to have a consideration. Should we make our back testing code event-driven or not? So essentially, do we have event-driven code versus a static environment for back testing? So with event-driven code, what tends to happen is you have a new data point coming in. It will then do some sort of calculation check whether we need to trade or not. If not, it will continue running, etc. So in a live environment, event-driven is probably quite good, particularly if you're trading high frequency. And when you're back testing, what you can do is you can just speed up this loop and just feed it historical data. So essentially, your code for the back test and your code for execution will be very similar, essentially. The difficulty is the looping nature of this can make it slower in a language like Python, unless you use some tricks like number, essentially. And essentially, if we do our vectorized operation in Python, it's going to be a lot quicker than continually using loops without some funky number coding. So at present, what I've decided is that FinMarketPy is primarily driven as a research environment, and we're going to try and keep it that way, essentially. I might end up adding event-driven code in the future to facilitate live trading strategies, but it's not really my focus. And the library is designed more for low-frequency strategies rather than using like massive amounts of tick data, essentially. But yeah, you never know. Maybe I might end up adding live execution to it and event-driven stuff as well. So we'll see. I have some of my own closed source code for executing stuff with interactive brokers. I probably will end up open sourcing that, but I need to test it a bit more, I think. Okay, so I've got a question here. Are there Python packages that let you download futures data from LME? I'm not sure in terms of LME what type of Python environment they have actually, Python APIs that they have, but I'm sure there must be, because LME data is also available through Bloomberg though as well, and I think through Refinitiv. So there's definitely an API for Bloomberg for getting futures data. So yeah, I would have thought it's paid. I don't think the data on LME would be free. So even if you get it directly from LME or you get it from a vendor like Bloomberg, I don't think it will be free, unfortunately. Yeah, actually some stuff traded on exchange is free. So you can get free equities data, I think. But you won't be able to get, I don't think you'll be able to get high quality free futures data. But one source for futures data, which is not too expensive, is Quandl. So I would recommend maybe having a look at Quandl potentially. So let's do a few demos for Python. I'm going to show you how to download a plot, market data plot with FinDataPy, also plotting with ChartPy as well. If we get a bit of time, maybe I'll also be able to show you my TCA app as well. I just need to start that in another window as well. Just to kick it off. Okay. Also how to plot a vol surface as well with FinMarketPy. And all my open source libraries, you can get them off GitHub, by the way. That's absolutely fine. Oops. Okay. So downloading and plotting market data with FinDataPy. So this is basically how you plot, how you get market data through FinDataPy. So this is one interface for doing it. So we import basically a market object, a market data request, a market data generator. We create a market data request, which basically shows us what data we want to download. So we want to download a week of data for euro dollar. We want to intraday data. The category is FX. You only want closing data, and our data source is going to be Bloomberg. So let's just do Shift Enter to run that. So I've basically got a Bloomberg terminal running in the background for this. In order to plot it, we import the chart object and the style object. The style object basically defines the properties of the plot. So the title, the width, the height, and so on. And then finally, we instantiate the chart object saying that we want to plot with matplotlib this data frame with this style. So if we do Shift Enter, let's run that. So we can see this is fairly live data. Obviously here we don't have data because of the weekend, essentially. So that's just a quick way of showing how you can download intraday data within DataPy for Bloomberg. If we want to, we can change our plotting library to Plotly just by changing the keyword here and without changing any of the rest of the text. There we go, and that's Plotly. Because it's Plotly, we can zoom in basically on the chart as well and play around with it like that. We can even save it to disk if we want at the same time. We can also change our data source quickly. So in this case, as opposed to using Bloomberg, I'm using a free data source called Dukas Copy. So this is a Swiss retail broker, but actually the data quality is not too bad for their tick data. Again, the market data request looks pretty similar with a start date and a finish date. The difference is that we're getting tick data here, not intraday data, and the fields available only bid and ask data, essentially. We instantiate the market object here, and we fetch from the market our market data request here. So let's just do Shift-Enter to run that. That's just going to take a few seconds. And the nice thing with this is it's free data, by the way, and you can do your back testing on this, and it's definitely one of the key free data sources, I would say, for Bloomberg for FX high frequency data. There we go. So if we want to plot that data frame, we again instantiate our chart object. We say we want to use matplotlib. Let's plot that. Okay, there we go. So this is data, I think, from 2020 essentially. And the history goes back like 10, 15 years for this. So it's pretty cool. It's a nice resource. And I've spent quite a bit of time writing this API, so it's a lot easier to download than if you do it manually. That's next. It's also possible to make a call using a string for data for any supported data source and also for predefined tickers. So in this case, I basically say I want to get data from Bloomberg. My nickname for that data will be VIX, and the Bloomberg ticker is VIX index. And I want it to be 1 week. So this is just another way of fetching market data without creating that market data request, which I showed earlier. So if we do Shift-Enter, there we go. It's going to download that now from Bloomberg, basically, to the past week. We can do something similar as well. So this is for intraday FX data for Eurodollar, just using this string, which is basically like a ticker. And the nice thing with FinDataPy is it has predefined tickers. So for FX, I've got a predefined ticker in a CSV file. So this is a proxy essentially for Eurodollar currency, which is the underlying ticker on Bloomberg. So if we do Shift-Enter, there we go. So then that's showing you another way to download intraday data from Bloomberg. The next thing I want to show is a very quick demo of my TCA library. So essentially, transaction cost analysis involves looking at your trade data alongside market data, which uses a benchmark. And it's basically a way of understanding how much you're paying for trades. So I've got here in these, I've got a private question. In your Python modules, do we have to download it via GitHub, or can we easily call it in via the usual Jupyter module with an Anaconda using import? So the key point is you need to do pip install first of all in order to download it, and then you can import it basically. So that's the key. You need to do a pip install like FinDataPy or pip install FinMarketPy first before you can import it essentially. So basically, transaction cost analysis is a way of understanding how much you've paid your broker to do your trades. And you need two data sets. One is trade and order data, which is basically your executions. The second thing you need is market tick data. This is going to be very dense, large data sets, essentially. And it involves a lot of heavy computation, and I've used like a lot of tips and tricks basically to speed it up. You can either call this through the Python code, or it also has a GUI built into it as well. So I'm going to do a quick demo of this. Oops. There we go. Okay. And all this code is on the GitHub site for this GUI as well. So this GUI is actually being written in Dash. and Python. So we basically select the start date and the end date for our trades. There we go. Then we do calculate here. Just going to check. I'm just looking at the other screen to see the calculations in the background. There we go. It took 5 seconds. There we can see all of our orders that we've executed. We can zoom in. We can see it's redrawn the plots. We can click on our orders to see the price before and after. There we go. That's the price before and after. And this gives us a distribution of our slippage. So our slippage is basically the difference between our mid-market benchmark and where we got filled. So that's usually a negative quantity if we're taking liquidity from the market. And we've split it up here to look at the distribution of the buy trades and also the sell trades. We can also look at execution level as well. We can zoom in, have a look. We can click on the trade as well, and there we go. We can also look at the distribution of the execution as well. And we also have a markout which shows us the price before and the price move after, essentially. And to my knowledge, this is the only open source transaction cost analysis library out there. There might be others, but I'm not aware of any. But this is the only one, at least for FX, which is out there. So if you're interested in transaction cost analysis, or even if you just want to know how I've created all these charts and stuff, just take a look at this library on GitHub, basically TCAPy. And also let me just show you the website for TCAPy, by the way. So if you want to play with some of this code on on the GitHub site, if we go down to the bottom here, it's got some Jupyter notebooks that we can run on Binder in our own own browser. So we can, the 10-minute view of TCAPy, if we click run on Binder, that will actually create a Jupyter notebook instance on the cloud, and you actually can go through the code and run it within your browser directly. It usually takes a couple of minutes, but that's definitely something to have a look at if you want to play around with the code. In the interest of time, I'll just leave that going on the side, basically. It usually takes a bit of time to kick that off. There we go. And lastly, I want to show you how we can plot an interpolated FX volatility surface as well. So in this instance, I'm basically getting data for cable, so sterling against dollar, from the 23rd of June 2016 to the 23rd of June 2016. This is because this was a date of around the date of Brexit. The data is from Bloomberg, and I want to have FX volatility market data. So that will give me data for the FX implied volatility surface, FX spot, rates market, etc., and so on. So what we do is we instantiate the FX vol surface with that data frame full of all the market data. Then I extract the volatility surface across all the dates, essentially. And then I can plot it as well. So let me plot it here. There we go. So again, we instantiate the chart object, the star object. In this case, the chart type is slightly different. It's surface as well. And we can see that this basically shows us the FX volatility surface for sterling around the time of Brexit. And you can see here, basically, the implied volatility is a lot higher for downside in sterling compared to upside, because people were kind of afraid of a downside move in sterling during that period. And all of this underneath, by the way, this is quite complicated code underneath, but this is all open source. And I've relied upon a library called FinancePy for doing all the volatility surface interpolation. But typically, it's really fiddly to do this type of stuff yourself. So I've done a lot of that work for you by writing it. There we go. So other functionality is that you can come to the QDC basically to have a look at that in my Python for Finance workshop at the QDC. So why Python for Finance? Well, because it's easy to write and there's lots of tools. And admittedly, it's not the fastest language, but I would say it's pretty impressive in terms of what you can do these days with Python, because there's so many packages out there which reduce the cost to entry, essentially. There's many libraries like Pandas, I'd say the key one, NumPy as well, a lot of visualization libraries. Some of the ones that I've written for finance, for backtesting, stuff like MarketPy as well. So because so much stuff is out there, it makes it a lot easier for you to get started and analyze financial markets. I also talked a bit about developing libraries for financial markets and some of the thought process behind them, and how most data science problems are kind of similar in terms of their general steps. And lastly, we showed a few Python demos as well. So just showing you how to like download market data with FinDataPy, interpolating volatility surfaces as well. Also a bit on TCA-Py as well with the GUI. And there's obviously many, many more things that you can see. And I guess if you come to QDC, we'll go over a lot of this stuff in detail in terms of downloading market data, developing trading strategies as well, doing web dashboards and so on. So this is all going to be part of the QDC cohort next time, essentially. So if you've got any questions about the talk, I guess now is a good time to ask me. Or if you've got any questions about the QDC course as well, that I teach on the Python for Finance workshop, just let me know as well. I did get quite a few questions already in the chat, which I've answered. I hope there were none that I missed that were asked in the chat. I think I answered all of them in the chat. Okay. So I got a question here. A lot of the QDC seems to focus on algo trading. Are there other parts which focus on derivative pricing and trading? So I'd say most of it is going to be about algorithmic trading, but during my part of the module, I do talk a bit about volatility, doing volatility targeting and stuff like that when you're trading. So there will be a bit of stuff, but yeah, the focus is mostly on algo trading, because typically what you tend to find is that's not really taught as much, especially the module, say, on KDB. It's not really something that people teach quite as much, but it's just as important. And all these areas that we're teaching are basically areas where you can get highly paid jobs. So particularly in KDB, also Python these days, there's lots of jobs in Python as well. So we're trying to focus on areas where we think people can get definitely get good jobs in, and the same for C++ as well. I hope that answers your question. Okay, well, I guess let's just leave it for another 30 seconds, just in case anyone else has further questions.
Hi, I got a quick question. The demo that you showed for FinDataPy, was that using free data from Bloomberg, or was that making use of a Bloomberg API?
No, so underneath that's using the Bloomberg API. So you need to have a Bloomberg terminal, the Bloomberg API to run that. But through FinDataPy, you can download free data from Duca's copy, which I showed you for FX high frequency data. There's also Quandl, which is available in FinDataPy, which has quite a few free data sets. Not every data set on Quandl is free, but probably enough to get you started. Also, in terms of Yahoo Finance as well is also supported by FinDataPy for downloading stock data. So I got a question here. What more do I need if I have Python, C++ skills and a quantitative degree? I'd say that's definitely a good start, but also to understand the application of a lot of these programming languages. So what we try and teach is not just the coding itself, but also applications of that. So using Python within the context of developing a trading strategy, or using KDB potentially to basically have a look at high frequency data, essentially. I also got a question. What do you think is MATLAB as an alternative? MATLAB, I used MATLAB a lot actually when I was at Lehman. It's definitely a very good tool, and there's a lot of legacy MATLAB code out there. So it's definitely something worth looking at. But I think there is an issue in that obviously it's not open source, and maybe not as many people are learning it these days. So that probably counts against it. But ultimately, I know there's lots of people in institutions which still code in MATLAB. I've got a question. Do you use stats models at all, or do you think there's much better alternative? So I do use stats models actually sometimes. So particularly if I'm doing linear regression, sometimes I do them in scikit-learn, but in other instances I use stats model because it prints out all the summary statistics very easily. So for some purposes, I find actually stats models is better than scikit-learn in practice. I guess stats models are more written from the perspective of a statistician, whilst scikit-learn is more for somebody that's into machine learning, essentially. But ultimately, linear regression is, I guess, it's a form of machine learning, but it's kind of a classical statistical technique, I suppose. Okay. No, thanks for all your questions. Is it the case that for every possible data source that this code could download from a corresponding application terminal page for that data source must be open? It depends on the data source. So for example, for Bloomberg, I need to be logged into the Bloomberg terminal. For Quandl, it's just an API. So there's no Quandl application or anything on your machine. You just make an API call to Quandl, and then that will verify your identity through an API key. So it just depends upon the application. I think for Icon, you need to have an Icon terminal running, but it just depends on the vendor as to how you use its API. There's other APIs for Bloomberg which I don't think need the terminal, but they're more expensive. I got a question here. What is the lecturing type in QDC? Is it a Blackboard PPT style, or will we do live coding, etc.? I think that depends on the lecturer, but typically the way that I do it is through Jupyter Notebooks, and basically go through the code that way, essentially. But then my hope is later, I do also provide tutorial sheets as well. So if people want to code after the course, they can do to practice, essentially. Let's give it another minute or so for more questions. So thanks for all your questions. They're all very relevant for the talk. Okay, well, I guess if there's no more questions, I guess that's about it. And I just want to say thank you for taking the time out to come to the course, and hopefully see you on the QDC maybe soon. And any questions about the QDC, feel free to ask me. Or if I don't know, actually, WBS will probably have a better idea as well in terms of the timing and the scheduling for that as well. All right, thanks again. Thank you.